Hello and welcome to some molecular geometry practice problems. Let's do it. We are going to start with water. So for step 1, when you want to get to your molecular geometry, you have to start with drawing your Lewis structure for the molecule. So for our Lewis structure, we are going to write the skeleton first. So we have H2O, so that means we have 2 hydrogen and 1 oxygen. And we know that when we write our skeleton from our previous Lewis structures, you should know this by now, your hydrogen are always going to go on your terminal ends, and thus oxygen is going to be your central atom. If hydrogen is not present, you put your more electronegative atoms on the outside and the less electronegative as your central atom, just as a review. We are then going to sum all of our valence electrons. So on our periodic table, we can find that hydrogen has 1 valence electron, oxygen has 6 valence electrons. We need to make sure we sum all of them, so that means you multiply hydrogen by 2, and that is going to get you to 2. So our sum is going to be 6 plus 2. Ooh, I wish that was a better plus sign. And that's going to get us to 8 total valence electrons. So now we're going to draw our line to show the sharing of 2 electrons. So instead of writing 2 individual dots right here, I'm just using a line, and the line shows 2 electrons. Now, step 4, we are going to add our remaining electrons to satisfy our octet. So to figure out how many electrons we have remaining, we're going to subtract how many electrons we used to bond the atoms. So that is 8 minus 4, which gives us 4 electrons left. And so we are going to satisfy our octet rule. We're going to look at this hydrogen. Hydrogen has 2 electrons being shared with it, so it has got a full valence shell because hydrogen follows its duet rule. So hydrogen's good. We're going to look at this hydrogen. This has its 2 valence electrons, so it's good. And so oxygen, if we look, oxygen has 2 electrons, 4 electrons, so it still wants 4 more, and good for us. We still have 4 electrons, so we're going to write in our 4 electrons. And that is your Lewis structure for water. Now, the next step is we need to predict the electron pair geometry. So our electron pair geometry is going to count all the electron domains. So this is the tricky thing about water, is when it's being written out to determine its shape, the lone pairs that are on that oxygen are going to want to actually push as far away from the bonded atoms as possible. So this is more of the shape that ends up taking place. So if we were to just say, okay, what is our electron pair geometry? And we counted all of our electron domains here. I'll go ahead and maybe I can highlight each of our electron domains here. We have 1, 2, 3, 4. So we have 4 electron domains, and if you have 4 electron domains bonded to a central atom, that by default would be a tetrahedral. I'm not going to write out the full word because it's actually really hard to do with the mouse. But you should know this is a tetrahedral. That is for the electron pair geometry. So guys, remember, this is not your final step for figuring out your molecular geometry. This is your electron pair geometry. So this is kind of your intermediate step. And now I'm going to ask you to find your molecular geometry. So I'll draw a little arrow. The molecular geometry, it only counts our bonded atoms. So we are going to rewrite this, and we're only going to draw out our bonded atoms. But I'm going to draw it with the same shape as I did the electron domain, because although we are not counting, we're not actually counting these lone pairs, we're like pretending they don't exist. Well, I guess we're not pretending that we don't exist. We're just pretending we can't see them. They're still causing a repulsion effect. And so that repulsion effect is going to cause water to be a bent molecule. So the overall answer for what is the molecular geometry of water, you would say that it is bent. And that's because we only count our bonded electron domains. So these two domains. And so therefore it is a bent molecule. But remember, the reason you have to do your electron pair geometry first is because you need to remember that these lone pairs are there and they're causing it to be bent. And that is why you need to do a good Lewis structure. So it all goes together. Our next molecule is going to be dihydrogen. So dihydrogen, we start by writing its skeleton. There are only 2 atoms, and they're both hydrogens. So there isn't really like a central atom. You just write them side by side. We're going to sum the valence electrons. So we're going to say hydrogen. We know based on the periodic table it has 1 valence electron. We are then going to multiply that, if I can draw an X, we're going to multiply that by 2 because there are 2 hydrogen and you need all of your valence electrons. That's going to get you to 2 valence electrons. And then in step 3, we're going to draw a line between each bonded atom to represent the sharing of 2 electrons. And we take away the amount of electrons we just used, which was 2, because that line represents 2. And we're at 0. And we're done. Isn't that great? That is the correct Lewis structure for dihydrogen. Now we're going to go to the next step. We want to predict its electron pair geometry. So I'll draw an arrow here. Its electron pair geometry is going to count, I'll write it out again. It's going to count all of its electron domains. So the question is, how many electron domains does it have? It has 1. There's only 1. There's no lone pairs, there's nothing else, just 1. So with 1 electron domain, that means the molecule is going to be linear. And so that is its electron. Ooh, boy, that is a rough looking linear word. Oh dear. But it's linear. That's its electron pair geometry. But that's not the final step. The final step is its molecular geometry. So the molecular geometry, again, it only counts the bonded atom. So the good thing about this is there are no other electron pairs, so it's the exact same thing. It is a linear molecule. I'm not going to rewrite the word linear. So your molecular geometry for dihydrogen is a linear molecule. All right, methane. We are going to write out its skeleton. So we know carbon is going to be your central atom because the hydrogen are always going to go out on the terminal ends. And the hydrogen are going to spread out in a cross formation because they don't want to be clumped together due to the repulsion between electrons. And we're going to sum all of our valence electrons, step 2. So carbon, we know carbon has 4 valence electrons. Hydrogen has 1. We are going to multiply that 1 by 4 since there are 4 hydrogen total. And so our sum is going to be 4 valence electrons from carbon plus your 4 valence electrons from all 4 of your hydrogens, and that's going to get us to 8. We are now going to do step 3, and we're going to draw a line between each bonded atom to represent the sharing of 2 electrons. So each line represents 2. So that means we just used 8 valence electrons, because if you were to count them all, it would equal 8. And that gets us to a nice tidy sum of 0. So that is your correct Lewis structure for methane. So then for your predict your electron pair geometry, we're going to just kind of use this Lewis structure up here. So I'm not going to really rewrite it here. I'm going to highlight every electron domain that I see. So 1, 2, 3, 4. I see 4 electron domains. And because there are 4 electron domains, that means this molecule, the shape is going to be tetrahedral. Oh dear, that A is really small. Tetrahedral. I'm not going to write out the rest of it. So it's going to be tetrahedral, and we're going to go to step 3. We're going to predict its molecular geometry, and that is where you count only the bonded atoms. Well, we are in luck. This carbon only has bonded atoms to it. It does not have any lone pairs. So again, it's going to be tetrahedral. So I'm going to try to draw that shape out for you. Not that you, So we're going to, like a ball and stick kind of model. It's almost like, imagine each of these lines are like a stick, and they have a ball attached to it, which is the other atom. So you have hydrogens here, and then we're going to try to draw this dotted line out here, and that's kind of showing that it's in a 3D shape. It's going behind it. So this is a tetrahedral molecule, and you're going to have the hydrogens, the bonded atoms are spread out as much as they can from one another, and your bond angle, which you don't actually need to know, but it's just, it's there. It's a 109.5 bond angle. 109.5. This is carbon bonded to 4 hydrogen. Okay, yeah, that was kind of lame. But it's a tetrahedral molecule. And that's just a picture of what that tetrahedral looks like. Ammonia. We are going to write out its skeleton. So nitrogen is your central atom, because your hydrogen are going to be always on the ends. So we have hydrogen, and we're trying to make sure hydrogens are spread out around the nitrogen. They don't want to be too close to one another. Okay, and then we're going to sum our valence electrons. So nitrogen has 5 valence electrons. Hydrogen, if I can get that right. Hydrogen has 1. We're going to multiply that by 3. Because there are 3 hydrogen, we get a total of 3. And then we're going to do our sum total of all the valence electrons in this molecule. So 5 plus 3 is going to equal 8. So we have 8 valence electrons to work with. So we're going to go to our next step, where we're drawing a line that represents the sharing of 2 electrons between your central atom and the atoms all on the outside. And so we did that, and we're going to say, okay, we just used 6 valence electrons when we did that, since each line represents 2. So we have 2 electrons left. So now we need to go to step 4, add remaining electrons to satisfy octet. So we're going to look at all of our outside atoms first. This hydrogen, it has 2 electrons, so it has a full valence shell. It's met its duet rule. It's good. Hydrogen, same here, 2 electrons. Hydrogen, 2 electrons. It's going great. So all these 3 hydrogens have full valence shells and are completely stable. This nitrogen will count. It has 2, 4, 6. It has 6 valence electrons. It wants to get to a full octet, meaning it wants to get 8 electrons. And so we are going to add a lone pair up top here, and that'll bring us up to 8 valence electrons for nitrogen, and we'll make sure we subtract that from the total we've been keeping track of, and that gets us to a nice tidy sum of 0. And so this, my friends, is the correct Lewis structure for ammonia. Now, next step, we are going to predict It's electron pair geometry. So we have to identify all of its electron domains. So that includes your bonded atoms plus your lone pair. It includes it all. So that's 1, 2, 3, 4. So since it has 4 domains, its electron pair geometry with 4 domains, anything that's going to have 4 domains is going to be tetrahedral. Tetrahedral. Again, not writing the full word out. And now, this is interesting. This is going to be different. The molecular geometry, remember, molecular geometry, key here is it only focuses on bonded atoms. However, this lone pair of electrons is going to affect its overall shape, even though we're not going to draw those. So when we draw out ammonia, sorry, I should have drawn N up here, H, it is, that H is looking wonky. It is going to have a bent flavor to it. So there are these up here, basically these invisible lone pair of electrons that is trying to push as far away from these bonded atoms as possible. So it's going to push those away, which is going to lead you to having this shape. It's going to be a trigonal. I'm honestly just going to write trigonal, like trig. You're going to have to fill in the blanks. Trigonal, and it's called pyramidal. Pyramid. Oh dear, this is complicated. Okay, seriously, you're just gonna have to look up the spelling because I'm not gonna write the whole word out with my little finger. All right, this is a trigonal pyramidal shape, and that is its correct molecular geometry. And the reason it's trigonal pyramidal and not tetrahedral or not trigonal planar is because the tetrahedral would be only for the electron pair geometry because it counts this lone pair. And the reason it's not a planar, where all these hydrogens would be on the same plane and more spread out around the nitrogen, is because although we're not actually representing the electrons, they're still there and they're still causing a repulsion. So this would be trigonal pyramidal. We are on to phosphorus hydride. So we're going to write out its skeleton. So we start with a phosphorus, and then we put the 3 hydrogen spread out around it. Then we are going to sum the valence electrons. So you find phosphorus on your periodic table. You find out that it has 5 valence electrons. Find your hydrogen. It has 1 valence electron. And there are, make that a multiple sign. There are 3 hydrogen. So we're going to multiply its 1 by 3. And then we're going to do the total sum. So that's 5 plus 3. And that is going to equal 8. Great. And so now we are going to connect our bonded atoms. Each line represents 2 electrons. So that means we just used a total of 6 valence electrons. That gets us to 2. And so we check our outside atoms first. And we say, okay, do they have their full octet? In hydrogen's case, does it have a full duet? And the answer is yes, because this hydrogen is sharing these 2. This hydrogen has these 2. This hydrogen is sharing these 2. So that leaves us with phosphorus, and phosphorus has 2, 4, 6 electrons in its orbit. So it's going to want 2 more to reach its octet, and that gets us, oh, those are not very good lines. I'll draw our two. It's our lone pair up there. It's supposed to just be two dots. And that is your correct Lewis structure for phosphorus hydride. And now we are going to predict our electron pair geometry. So we're going to count all of the electron domains. All the electron domains, so that includes lone pairs and bonded atoms. So this phosphorus hydride has 4 electron domains. So its electron pair geometry would be tetrahedral. So I'm just going to write out tetra, and you can fill in the blank for the rest of the word. Tetrahedral. Now, its molecular geometry is going to only, remember, it only counts the bonded atoms. So it's not going to count that electron pair. So we're going to write it out here. And the hydrogen, they are actually going to be repelled by that lone pair of electrons, even though we're not representing it. They're being repelled still. And so these hydrogen are not all on the same plane. They're kind of like a little bit down and to the side because they are being repelled by this invisible electron pair up here that we're not actually representing, but it exists. And so this shape is going to be called a trigonal, you can fill in the rest of the word, pyramidal, just like your ammonia from the previous page. All right, on this page, you're only going to get me to say pura because I don't want to write the rest of it. That's hard. The little mouse. Cool. Boron iodide. Oh, good old boron iodide. All right, so we're going to start with writing out our skeleton. Now, this does not have any hydrogen, so how do we know what goes on the central atom and what is on the outside? Oh dear, I just went ahead and wrote. I was starting to write hydrogen. How we know what goes on what sides is the more electronegative atoms are on the outside. Iodine is more electronegative than boron. So iodine goes on the outside. We are going to draw a line we're going to sum up our valence electrons. So boron and iodine. Boron has 3 valence electrons. You just find on your periodic table. Iodine has 7. 'Tis a halogen. And there are 3 iodine. So we multiply 7 by 3. And that is going to get us to 21. And then we do our sum total of all the valence electrons in the molecule. So that's 21 plus 3. And that is going to equal 24 valence electrons. All right, we are now going to draw a line to connect all of our bound atoms. And that's 2, 4, 6. That each represents... the line each represents 2 electrons, and so total that's 6 electrons that we just used up. So that leaves us with a leftover of 18 valence electrons. So we're going to add remaining electrons to satisfy octet. So we're going to start on the outside elements, the ones that are more electronegative, and we're going to fill in their octet first. So that's 1, 2, 3, 4, 5, 6, and then the line is 7, 8. So this iodine is good. 1, 2, 3, 4, 5, 6, and then the shared electrons between boron and iodine is 2, so that's 8 electrons, so that's good. And so we just used, I should have been keeping track. We used 6, 12. So each time we kind of fill up one atom's octet, we should probably just do the math. So that was, we used 6 there, and then we used another 6 electrons. Oh dear, we're running out of space over here, so I'm going to write up here. That means we have 6 electrons left, which is great, because once I use these 6 electrons to make iodine's full octet. Now we are at a total of 0 electrons. So when you're looking at this atom, you're like, whoa, whoa, whoa. You're like, boron doesn't have a full octet. So does that mean that we need to add a double or triple bond? The answer in this specific case is no, because boron is happy with 3 bonds. It is one of the exceptions to the octet rule. So now we are going to predict its electron pair geometry. And to predict its electron pair geometry, you're going to count all of its electron domains. So that includes any lone pairs and bonded atoms. And so boron does not have any lone pairs, and it has 3 bonded atoms. So with 3 electron domains, it is going to be a trigonal planar. A trigonal planar. Oh my. I promise I write a lot better in real life, but not by much. Okay, so that's a trigonal planar. And what that's going to look like, a trigonal planar, I'll write it next to it, is you're going to have boron, and basically your iodine are going to try to spread out from one another. The electrons on those iodines are repulsing each other. And so the farthest they can get from one another, the largest bond angles they can all equally form is going to be, it's going to be 120 degrees. So again, you don't need to know your bond angles, but what I'm trying to get you to understand is that the repulsion, it's spread out as far as it can possibly get, equally all around. So now that is kind of what it looks like on your electron pair geometry. We're going to predict its molecular geometry. We're going to count only the bonded atoms. So if we look back up at our Lewis structure, there is no lone pair. There's only bonded atoms. So that means, in this case, our molecular geometry and our electron geometry are going to be exactly the same. They're going to both be a trigonal planar. So they're both going to be this shape up here, a trigonal planar. Last, but certainly not least, is germanium fluoride. So we're going to write its skeleton. So fluorine is the most electronegative element on the entire periodic table. And so that is going to be written on the outside. Germanium is going to be your central atom. We are going to sum its valence electrons. So you want to find germanium and you want to find fluorine on your periodic table. Germanium has 4 valence electrons, and fluorine has 7, because fluorine is a halogen. Now there are 2 fluorines, so we're going to multiply that 7 by 2. That's going to get us to a total of 14 valence electrons with fluorine. And so a sum total is going to be 14 plus 4. And that is going to get us to 18. So that's our sum total of all of our valence electrons. And now we're going to go to step 3. We're going to show the bonds between beryllium and fluorine. And that bond is a sharing of 2 electrons. So we just used up 4 of our 18 valence electrons. So that leaves us with 14 valence electrons left. And now we're going to go to our most electronegative elements first and fill in their octet. So that's going to be starting with fluorine. Filling in its octet, we used up 6 valence electrons because it also has a shared pair. So that means it has a total now of 8 valence electrons around fluorine. So 14 minus 6 is going to be, it's going to be 8. All right, and then we're going to come over to this other fluorine. We're going to fill in its valence shell so it has a full octet. So we just use another 6 electrons. Remember that line represents 2 shared electrons, so fluorine now has 8. So we have 2 electrons left, and so we're going to come into the center, germanium, and we're going to give germanium 2 electrons. So we need to see, is germanium satisfied with its octet role? So let's look here. Germanium, we know both of the fluorines do. We just filled in their octets. Germanium has 2, 4, 6. It is not satisfied with its octet, and it is also not an exception to the octet rule. So that means we need to draw a double bond. So what we're going to do is we are going to erase one of these lone pairs off of fluorine. So I'm going to erase that top pair. And so now this fluorine only has 2, 4, 6 valence electrons. And instead of having that lone pair there, I'm going to actually share it between fluorine and germanium. And that way, fluorine now has a full octet because it has 2, 4, 6, 8. And let's look at germanium. Germanium now has 2, 4, 6, 8. Germanium has an octet. Everybody has an octet. And this is your correct Lewis structure for germanium fluoride. And so we are going to predict its electron pair geometry. The electron pair geometry is going to count all of the electron domains. Now, this is the first one we did with a double bond. Remember, a double bond, even though there's 2 of them right there, it only counts as 1 electron domain. So that's 1. This is 2, 3. So it has 3 electron domains. And so if it has 3 electron domains, its electron pair geometry is going to be the trigonal planar. It's a trigonal planar because it would have these 3 domains. Trigonal planar. Now that is not the final step, guys. That is your electron pair geometry. We want to know what is its molecular geometry. So the molecular geometry, we're going to write it out. We're going to rewrite our molecule here. So we have germanium, and we aren't going to write out that lone pair that's on top of germanium, but we do know that it still exists and that it's actually pushing against these fluorines. So the lone pair that we're not seeing is going to push, it's going to repel away, as far away as it can, from these bonded atoms. So here, I'll rewrite up here next to your trigonal planar. So I'm going back up to the electron pair geometry, and I'll just write it out here, which probably would have been helpful so you can see the shape. So this is going to kind of be its own shape up here in your electron pair geometry. But because our molecular geometry only counts our bonded atoms, it's only going to look at these guys right here. It's not going to look at this lone pair. So for germanium fluoride, this would end up being, its molecular geometry is a bent geometry. Because there's 3 atoms, there's 1 central atom and 2 atoms bonded to that central atom. And there's that lone pair that's causing this repulsion, although we don't draw it. And that ultimately results in a bent molecule. And that is all of your practice problems.